hace un honor, es todo un reto poder estar dirigiendo este centro que está enfocado a la investigación en vacunas y bioterapéuticos para uso humano. Y bueno, en términos de líneas de investigación, a grosso modo, trabajamos con nanotecnología aplicada en salud, el desarrollo preclínico de vacunas bioterapéuticos, de manera general con varios proyectos de investigación de diversos investigadores. Hoy platicaré pues, un poco lo que hemos comentado con el doctor Pierre y con la doctora Tatiana, de bioprocesos en terapia celular y génica. Decía yo, no me dedico a la parte, pues, nano como tal, desde el punto de vista de interacción celular con andamios, matriz extracelular, etcétera, pero digamos hay mucho potencial ahí desde mi punto de vista. Entonces, pues básicamente trabajo con células troncales que pueden tener diferente origen. He trabajado con células troncales embrionarias de ratón y humano, con células pluripotentes inducidas, con células multipotentes o unipotentes. Este gráfico, pues es un gráfico muy conocido, básicamente dependiendo de dónde tomemos nuestra fuente de células, será su potencialidad, siendo totipotentes cuando están en etapa de módula, y en cuanto comienza, digamos, el desarrollo embrionario y la especialización de los tejidos y órganos, pues se va perdiendo esta potencial de autorreplicarse y diferenciarse a las diversas capas germinales o tejido específico. He trabajado, decía yo, con pluripotentes, multipotentes y unipotentes, y aquellas que también conocemos como pluripotentes inducidas, que son las que a través de una manipulación en el laboratorio podemos regresarlas de un estado diferenciado a un estado pluripotente esencialmente. La importancia del uso de las células troncales con respecto a su posible aplicación o expansión en el laboratorio, pues tiene que ver con aquello que nosotros podamos utilizar para hacer los cultivos. Tradicionalmente se hacen cultivos bidimensionales, sin embargo, a pesar de que han sido ampliamente utilizados, ampliamente también eficientes, no necesariamente representan lo que sucede en vivo, ya sea en un estado patológico o un estado fisiológico normal, de funcionamiento normal, ¿no? De esta forma, pues se ha avanzado a nivel internacional en diversas metodologías para el cultivo tridimensional o en forma más compleja de aquello que sí representa lo que podría estar sucediendo en vivo, ya sea en un estado patológico o en uno no patológico. De esta manera, pues se ha avanzado con bioimpresión de hidrogeles, cultivos en bioreactores con sistemas altamente controlados o no controlados, como el caso de los matraces, y en el cual nosotros podemos hacer justo la expansión masiva o identificar y poner, digamos, a las células en un sitio específico rodeada de algunos factores de crecimiento que nos permitirán mimetizar lo que sucede en vivo, ya sea en organogénesis o bien en un estado fisiológico o patológico. De tal forma que con estas estrategias podríamos nosotros tratar de replicar aquellos procesos complejos de interacción célula-célula o diferentes tipos celulares o diferentes componentes, ¿no? De tal forma que en ingeniería tisular, que es lo que nos permite hacer estos experimentos, se utilizan principalmente células troncales, andamios que nos permiten ser estos andamios tridimensionales y factores de crecimiento, que son aquellos que nos permitirán integrar a las células cuando uno hace la siembra, ¿no? El cell seeding, pero también controlar un poco la diferenciación y la expansión e interacción, si fuera el caso en tridimensionales. Hablaré rápido de unas pruebas preclínicas y clínicas que hemos hecho. En este caso fue en un ratón, en un grupo de ratones, obviamente, en el cual se ligó esta vena, que es la que, digamos, integra el flujo principal sanguíneo hacia el miembro inferior. De esto lo hicimos tratando de mimetizar una enfermedad que se llama isquemia en miembros inferiores. Aquí lo que tratamos de hacer es tratar de identificar si solo la interacción de una aplicación de terapia celular era suficiente o si esto podría ser enriquecido con factores de crecimiento, sobre todo en este caso antiinflamatorios. Lo que encontramos es que esta estrategia tenía, si poníamos solamente a las células con respecto a las células con plasma rico en plaquetas, pero al plasma rico en plaquetas identificamos cuáles eran los factores, TNF-alfa, VEGF. Claramente VEGF iba a tener un mayor impacto en la generación de esta neovasculatura. Toda esta parte de aquí son vasos sanguíneos nuevos que se formaron a partir de la terapia, ya sea con células mononucleares solas o con células mononucleares enriquecidas con estos factores en específico. Lo que logramos fue encontrar una reperfusión en ese miembro isquémico que habíamos nosotros generado de manera artificial. Esto lo llevamos a una aplicación en humanos. Por supuesto, nosotros hacíamos solo la parte de recuperación, proliferación celular, y los clínicos hacían la parte de interacción con los pacientes y de trasplante per se. Y aquí vemos cómo las estrategias que nosotros planteamos, pues sí tienen un impacto, digamos, en este es el flujo sanguíneo en un pie que teníamos, bueno, en extremidades inferiores isquémicas, no solo un pie, es un grupo de pacientes como tal. Si bien digamos, hay podríamos criticar, ¿no? Un poco las desviaciones estándar, la verdad es que a grosso modo, pues sí hay un beneficio para los pacientes que fueron tratados con esta estrategia experimental. Después pasamos a una segunda estrategia experimental, en este caso fue con tejido isquémico cardíaco en pacientes que tenían ya programada una cirugía, no por este caso, sino por algún otro tema del corazón, pero que se había identificado que tenía lesiones o regiones en donde no tenía flujo sanguíneo, que lo vemos aquí en el estado basal. Lo que está en rojito es un poco lo que sí tiene flujo, y lo que no tiene rojo, pues aquellos tejidos, parte de tejido en donde no había flujo sanguíneo. Se hizo un trasplante de células, hicimos comparación, ahora sí hicimos digamos, una purificación específica con ciertos marcadores que, de acuerdo a la literatura, nos permitirían que estas células migraran al sitio que tenía esta lesión isquémica y se integraran y proliferaran formando vasculatura. Es un poco lo que esperamos a nivel teórico, y lo que sucedió, que por supuesto no lo pudimos ver a nivel tejido, pero sí en términos del flujo sanguíneo, pues fue que después de 6 y 12 meses teníamos una mayor flujo sanguíneo en las áreas en donde no teníamos antes, como lo podemos ver visualmente en estas regiones. Decía yo, estos en pacientes. Hemos trabajado también tratando, es importante para nosotros en el laboratorio tratar de optimizar los medios de cultivo y esto que tenga efectos en la optimización de la diferenciación celular cuando hablamos de células troncales pluripotentes. En este caso, en términos de neurogénesis, estuvimos utilizando, enriqueciendo al medio de cultivo con alfa-tocoferol y el ácido ascórbico, y revisando cómo estos podrían tener un impacto en la generación del número de axones, en el tamaño de las rosetas neurales y en el diámetro también del número de los axones como tal, ¿no? Entonces, lo que encontramos es que sí teníamos un efecto en comparación con el control, aunque, digamos, en algún momento, por ejemplo, el diámetro de las rosetas llegaban al mismo valor del diámetro como tal. No así en la longitud de los axones y un poco también en el diámetro de los axones, que por supuesto tendríamos nosotros que posteriormente revisar cuál es el impacto a nivel de funcionamiento. ¿Por qué lo hacemos? Pues porque la intención es que estos proyectos pudieran eventualmente tener alguna utilidad en términos de aplicación clínica, esperemos, o preclínica, y estas aplicaciones podrían ir desde aquellos modelos en los que se hace trasplante celular, o bien modelos en los que nosotros hacemos un control del cultivo. En este caso anterior es cultivo tridimensional, tratando de modular el número de células que integramos para controlar el diámetro de la roseta neural en un cultivo tridimensional, o bien cómo integrar a las neuronas en una red de nanofibras compuestas de colágenos y o fibrina, o una mezcla de ambos, tratando de conocer si estas neuronas se integran a las nanofibras para que eventualmente podríamos nosotros trasladar este parche, si quisiéramos decirlo de alguna forma, a un modelo de daño en médula espinal seccionada, ¿no? Aquí vemos en rojo, vemos a los axones de las neuronas que nosotros cultivamos sobre las nanofibras, y en azul vemos a las nanofibras como tal, que por supuesto es una red mucho más densa que las neuronas, ¿no? Los axones de las neuronas. Otro de los proyectos en los que de hecho interactuamos con la doctora Tatiana, con el grupo de laboratorio de las Biodit, es el diseño de un sistema de microfluidos que nos permitiera cultivar a 3 especies diferentes de estirpes celulares, en este caso a unas células que son derivadas de glioblastoma humano, a células astrocitos y a células que generan, que también en los 3 casos son derivadas de humanos, que generan microvasculatura. Entonces, nuestro diseño era básicamente tener 3 canales, en uno de los canales, más bien en cada uno de los canales tener un cultivo puro de estas células que acabo de mencionar, pero además entre ellos tener canales que intercomunican para poder evaluar justo cómo se comportan estas células durante el cultivo de las mismas. Bueno, pues aquí vemos una serie de fotografías que representan al cultivo celular. Teníamos, decía yo, en la parte superior, que lo podemos ver aquí, en la parte superior a las células de glioblastoma, en la parte intermedia a los astrocitos y en la parte inferior a las células endoteliales, en los 3 casos derivadas de tejido humano, cadavérico por supuesto, o en el caso de las células de glioblastoma, pues tejido de alguna resección quirúrgica, parte de tratamiento. Lo que encontramos fue que nuestras células podrían tener interacción y migración en el caso de las células de glioblastoma de un canal hacia otro a través de los canales de intercomunicación. No tengo a la mano los datos del canal de intercomunicación, pero era mucho menor el diámetro que el diámetro reportado de las células de glioblastoma, lo cual implica que podríamos tener ahí algún análisis secundario para revisar y proponer algún índice de migración celular. Este es solamente un ejemplo de cómo hacemos el cell seeding, que nos costó pues bastante trabajo para poder llevar a cabo. Tuvimos que jugar con las presiones, con el número de células, el volumen en el que se sembraban. Teníamos que sembrar primero a las células endoteliales, esperar a que generaran el endotelio para mimetizar un poco la barrera hematoencefálica. Básicamente esto sería tratando de mimetizar de manera muy limitada, tengo que reconocerlo, las interacciones entre las estirpes celulares en un microambiente tumoral, que en este caso pues todas son células de humano. Y este es un poco cómo se vería en la siguiente, perdón, en esta, cómo se verían progenitores. Aquí en este solo hicimos el cultivo de progenitores para evaluar la proliferación, progenitores dentaurales, perdón, para evaluar la proliferación y migración, diferenciación también de estas células neurales. Otro de los proyectos en los que estamos participando es en la generación de células de linfocitos T modificados para generar CAR T-cells. En este caso hicimos un proof of concept, ¿no? de CAR CD33 que estarían dirigidos a leucemia linfoblástica, y básicamente es solamente la estandarización del método. No estamos en este caso pensando todavía, y creo que nos faltaría mucho, es necesario reconocerlo así, para una aplicación clínica. No estamos en esa etapa todavía, pero sí estamos en la etapa en la que establecimos la metodología para generar las CAR T-CD33. Hicimos el reto con unas células de neoplasia, en este caso las células RE, jugando un poco con las concentraciones del número de células, el tiempo de cultivo, etcétera, y revisando si existía o no una respuesta a nivel inmune. También tengo que reconocer que, digamos, limitado, pero que sí existía esta respuesta inmune al hacer el reto entre las células CAR TC33 que diseñamos y construimos. contra las células de leucemia, ¿no? Voy a hablar muy rápido. Lo quiero comentar porque me parece que aquí es donde podría incluso haber algunas interacciones también, en este caso, análisis desde el punto de vista eh, de mecanotransducción, por ejemplo, ¿no? Uno de los proyectos que tenemos más avanzados y que ya llegaron también a la parte preclínica y clínica, no como sustitutos vasculares, pero sí como terapia celular, fue justo tratar de generar a precursores vasculares y células endoteliales ya completamente diferenciadas para identificar cuál podría ser el mejor método de aplicación preclínica o clínica. Estuvimos trabajando con células pluripotentes, en este caso troncales embrionarias de ratón. Diseñamos un método para hacer la diferenciación y expansión y especialización de manera óptima, jugando con la matriz extracelular, el número de células, etcétera. Comparando colágeno 1 contra colágeno 4, analizando la morfología, revisando si después de, por ejemplo, 600 horas de cultivo estábamos obteniendo microvasculatura, y en un análisis de microscopía electrónica identificar que existían estas interacciones entre las células endoteliales que conocemos como desmosomas. Desmosomas de las células endoteliales, el análisis de marcadores de pluripotencia o 3-4 y de diferenciación hacia células precursoras vasculares y células endoteliales como tal especializadas. Lo que encontramos fue, este gráfico me gusta muchísimo porque a expensas de estas células que nosotros sembramos, que son pluripotentes inducidas, es decir, OC3-4, hay una expansión inicial de estas células conservando la pluripotencia hasta 120 horas, y a partir de esta expansión, a expensas de este número de células, comienza una expansión de precursores endoteliales, y a partir de la expansión de esos precursores endoteliales comienza, bueno, en realidad continúa más bien, la especialización hacia células endoteliales, haciendo posible estos gráficos, calcular las velocidades de replicación, en este caso conservando la pluripotencia, y aquí con los dos marcadores de precursores vasculares, en este caso la velocidad específica para células endoteliales como tal. Es importante conocer que, bueno, a las 840 horas de cultivo teníamos sí especializadas, sí precursoras, pero también teníamos un número importante de pluripotentes, lo cual para una terapia, pues por supuesto no es deseable, ¿no? Esto lo pasamos ahora con células mononucleares, en donde se ha reportado que tenemos, en humanos, se ha reportado que tenemos entre 0.1 hasta 0.001% de precursores endoteliales en sangre periférica. Estos porcentajes van a variar en función de la edad y de comorbilidades que tenga el donador o paciente. Mientras más edad tengas, pues menor número de células progenitoras endoteliales, y con más comorbilidades también tendríamos una reducción importante. Lo cual significa que es todo un reto que a partir de las mononucleares podamos obtener a las células precursoras vasculares para eventualmente hacer una terapia celular. Lo primero que hicimos fue hacer la purificación, lo cual nos toma cerca de un mes, entre 15 días a 30 días, dependiendo, decía yo, de la edad, por ejemplo. Eh, pero nuestro método y medio optimizado nos permitía tener cerca del 90 o 95% de pureza en términos de precursores vasculares, que los identificamos con CD133 en este caso. No hicimos esta parte, pero la quise poner porque obviamente la mecanotransducción en las células endoteliales puede ser una buena forma de estudio con el modelo que estamos proponiendo, en este caso de células humanas. Lo que encontramos es que después del proceso de purificación y de expansión de las precursoras, hicimos un proceso de diferenciación y encontramos que aproximadamente en 30 días podemos encontrar o generar estas microvasculaturas en cultivo bidimensional, que decía yo hace un rato, es limitado en términos de si queremos hacer una aplicación clínica, por ejemplo, ¿no? Aquí, bueno, pues se ven muy bonitas las vasculaturas. Otra de las preguntas que teníamos es, si era posible generar un número suficiente de células, pero aquí tienes varias células, pero seguramente no serán suficientes para una aplicación clínica. La pregunta era cómo hacemos para generar un número suficiente, ¿no? Una producción masiva. Para esto utilizamos microcargadores, les llamamos, en donde adherimos un cierto número inicial y hacemos un cultivo básicamente, pero un cultivo en suspensión y tridimensional, y jugamos también con muchas condiciones para poder encontrar las condiciones específicas y óptimas que nos permitieran justo hacer esta expansión masiva. Que la vemos aquí en estas microperlas con las células adheridas. Una vez que hicimos este proceso de producción masiva, la pregunta era, por supuesto que estamos exponiendo a las células a diferentes revoluciones por minuto de agitación, lo cual cuando chocan estas microcargadores y las células que se van adhiriendo y generando, pues generan también unas fuerzas de corte que no calculamos, no hemos medido, pero que podrían tener un impacto en la capacidad de preservar su estado troncal, lo cual nos hizo, esta pregunta nos hizo analizar justo si teníamos preservada esta capacidad. Lo vemos aquí en esta figura, si la tenemos preservada. Y la siguiente pregunta fue si estas células cultivadas de esta forma podían conservar su capacidad de generar microvasculatura en cultivo bidimensional. Y bueno, vemos que sí podríamos tener estos cultivos y esta generación de microvasculatura, quiero decir, no controlada, bidimensional, y que creo yo que en este momento no tendría una aplicación clínica como tal. Por lo cual nos preguntamos si era posible integrarlas, después de todo lo que hicimos, a un sistema que nos permitiera llevarlas a una aplicación clínica. Pensamos un poco en los hidrogeles, hicimos el análisis de concentraciones de fibrina, en este caso, colágeno, o mezcla de ellos para hacer la reticulación y formar los hidrogeles, jugar un poco con las propiedades mecánicas de los hidrogeles y la forma en cómo sembrábamos a las células, ya sea durante su etapa en la que estaba como suspensión, o bien una vez que ya estaba formado el hidrogel como tal. Lo que encontramos es que en cualquiera de los casos era posible generar microvasculatura y era pues mucho más fácil llevarte un hidrogel y llevarlo a una herida que llevarte a los platos de cultivo estos que teníamos, en donde tendríamos que romper a las células y llevarlas otra vez a aplicación preclínica. Aquí, la verdad es que este me gustó muchísimo, pues si se puede ver, si no, bueno, me lo salto. Básicamente lo que encontramos en este hidrogel es que tenemos una vasculatura formada con unas de luz de 30 micrómetros, pero también tenemos a células que están en el proceso de diferenciación, como lo vimos en el gráfico con las cinéticas que habíamos analizado. Otra de las opciones que encontramos fue, para llevar una aplicación clínica, fue que generáramos andamios vasculares con nanofibras. Esto es un poquito cómo se generan las nanofibras, la morfología, diámetro, la caracterización, etcétera. Y el cultivo de las células endoteliales sobre las nanofibras. Una cosa que me pareció importante es que las células endoteliales se adhieren y adoptan, perdón, la linearidad que tienen las nanofibras como tal. Eso no lo vimos no lo hemos visto en las neuronas, pero sí en las endoteliales. Entonces también ahí podríamos encontrar algún punto de encuentro, ¿no? Para análisis. Generamos este andamio vascular que vemos aquí. Esto es una aorta de un grupo de ratas, solamente un ejemplo. La idea fue generar este andamio vascular con las nanofibras y sembrar, digamos, en la parte interna las células endoteliales. En la parte externa tendríamos que haber sembrado células de músculo liso, eso no lo hicimos, solo nos enfocamos en este caso a las endoteliales, y lo que encontramos fue que además de que sí era posible sembrar las células en la parte interna, tenía funcionalidad durante al menos 2 meses y medio aproximadamente estos sustitutos vasculares en los modelos animales que estuvimos trabajando. ¿Qué seguiría? La parte de aplicación clínica. Digamos, ya llevamos la aplicación clínica de células no purificadas con factores de crecimiento. de células purificadas, pensando en precursores vasculares, la expansión de estas células precursoras vasculares humanas, y lo que seguiría es, que está en nuestro radar, es la generación de estos sustitutos vasculares cultivados con células endoteliales para sustitución de alguna vasculatura en humanos. Por supuesto, necesitamos considerar diversas cuestiones regulatorias que tienen que ver con el manejo, derivación, expansión, etcétera, de las células precursoras vasculares como tal, y que en este caso se estarían pensando como dispositivos médicos más que como terapia celular cuando hacemos la combinación de estos dos elementos, que es el andamio vascular generado con nanofibras y las células endoteliales, que en este caso estamos pensando en autólogas, lo cual pues también es importante considerar los tiempos de derivación, purificación, expansión y diferenciación, si pensamos en pacientes usualmente pues geriátricos y con comorbilidades importantes. Con esto termino, me ajusté a los 30 minutos según yo, y pues con mucho gusto si tuvieran alguna pregunta. Repito, sé que no es digamos en el área específicamente de mecanotransducción, los estudios que hicimos, pero con mucho gusto espero poder contestar preguntas. Muchas
No,
gracias.
muchísimas gracias, Paul. Muy interesante. Además, como tú lo mencionabas al inicio, muestra muchas posibilidades de sinergia y de trabajo conjunto entre los diferentes grupos, ¿no? Y creo que lo que muestras en todo lleva mecanotransducción, como tú lo decías, por ejemplo, las células endoteliales sí sensan su sustrato y entonces acomodan su citoesqueleto justamente para después poder formar la tubería, digamos, que es muy diferente a lo que requieren las neuronas para sensar su matriz y tener una estructura diferente. Y como, aunque dices que no lleva mecanotransducción, tú nos diste ejemplos muy claros de cómo las células sensan de manera diferente su entorno, su matriz, y con ello adaptan a lo que tienen que hacer funcionalmente, ¿no? Entonces voy a tratar de buscar las preguntas de YouTube que nos han hecho. La primera que nos hicieron, espérame, esta modernidad, déjame, la busco, aquí está. La primera que nos hicieron es, para su chip axonal, ¿qué flujo se emplea y si requiere usar una bomba peristáltica? Supongo que la pregunta tiene que ver con que como estamos usando volúmenes pequeños, quizás eso aumenta mucho la presión interna en un chip y no sé, si pudieras platicarnos un poquito más en lo que busco las otras preguntas.
Pues todo, ese solo es yo le decía a mi estudiante, solo eso es un capítulo, porque en realidad yo le llamamos cell loading, ¿no? Como poner a tus células. Y tuvimos que jugar con muchísimas cosas, número de células, volumen, si poníamos flujo o no, si lo dejábamos estático. La verdad es que inicialmente consideramos poner flujo, lo hicimos, pero nos barríamos a todas las células, nos quedamos con dos, y terminamos haciéndolo estático, es decir, poniendo solamente el volumen inicial, eso dependerá del canal, pero pues por supuesto no más de medio mililitro, ¿no? Y lo que sí hacíamos es que poníamos unos reservorios al inicio y al final de los canales, en donde repetábamos cada cierto tiempo el medio de cultivo. La otra cosa que hicimos, que implementamos, fue que lo pusimos dentro de una, como una cubeta húmeda, ¿no? Ambiente húmedo, quiero decir. Por supuesto estéril, ¿no? Para que no se nos esfumara el medio de cultivo. Sí, inicialmente la idea es que se tuviera estos flujos. Lo que presenté no lo hicimos con flujos. A mí sí me gustaría probar ahora, porque además me voy a extender un poquito, pero es importante para los que hemos hecho estos cultivos, por lo menos para mí es muy importante. Terminamos reconociendo que era necesario primero generar microvasculatura que nos toma, dependiendo en qué etapa de la diferenciación pongas a tus células, pues te puede tomar 15 días, ¿no? Generar esta tubería o este andamio vascular. Terminamos poniendo primero esas, esperando esos 15 días, después poníamos el segundo canal, que eran los astrocitos o oligodendrocitos, y aquellas que crecen rapidísimo, que son las de glioblastoma, que tenías en una semana una proliferación masiva, pues las poníamos al final. Eso es un poco como los trucos que fuimos encontrando en el camino y que nos ayudó muchísimo para poder mimetizar esta barrera hematoencefálica o barrera hematotumoral, ¿no? Son preguntas muy importantes desde el punto de vista técnico que la verdad es que ayudan mucho.
Tengo varias preguntas, entonces voy a hacer dos y luego Pierre.
Sí.
A ver, en los organoides o cultivos 3D que desarrollan, ¿cómo controlan o cómo están seguros de los gradientes, por ejemplo, de oxígeno o de nutrientes? Esa es
Sí.
una. Y la otra te la hago después de esa.
Sí, está muy padre esa pregunta porque lo hicimos, lo de los organoides hemos trabajado más con neuronas y con células betapancreáticas para identificar el valor. Puedes hacerlo de dos formas, o haces una tinción para identificar HIF, o tienes que sacrificar unas rosetas neurales y haces tinción para identificar HIF, en el gradiente, o bien también hay unos microsensores, son unas agujitas que puedes poner a diferentes alturas. Por supuesto es exacto, ¿no? Digo, yo no tengo un sistema que nos permita como medir exactamente dónde vas a poner el sensor, pero sí es posible, en este caso sí es posible hacerlo así.
Y la otra pregunta antes de darle la palabra a Pierre es, ¿nos podrías contar sobre el proceso de validación preclínica y clínica de estas tecnologías?
Sí, es muy importante porque, mira, por ejemplo, los colágenos que usamos inicialmente para todas las pruebas fueron derivados de rata, pero después estuvimos utilizando un colágeno humano que es muy caro. Entonces, por supuesto, el colágeno al que tienes acceso desde el punto de vista comercial de humano, pues es para pruebas de laboratorio, es para experimentación, no es para pruebas clínicas. Entonces, esto lo digo por el tema de la validación, ¿no? Al final del día, la idea de proponer, por ejemplo, fibrina, es que pueda ser del mismo paciente o bien de donadores, ¿no? De estas bolsas que a veces ya no se usan en los bancos de sangre y que se pueden utilizar para aplicaciones novedosas como esta. Por supuesto, fibrina, desde el punto de vista fisiológico, pues puede tener alguna implicación negativa, ¿no? Porque recordemos que, por ejemplo, en neumonías se generan clots de fibrina que hacen una respuesta inmune negativa. Que no desearíamos. Entonces hay que revisar en dónde sí podemos utilizarla, que es, digamos, como la proteína que tendríamos de mayor acceso. En cuanto a las células, la idea es que sean terapias autólogas, pero vimos las repercusiones que puede haber, que tiene que ver con los tiempos de cultivo, porque estas terapias usualmente pues son, repito, en pacientes geriátricos, hipertensos, diabéticos, a veces oncológicos, etcétera, ¿no? Entonces la idea es pensar en terapias alogénicas. No hay mucho en endoteliales como halogénicas como tal. Esperaría yo que no hubiese, a lo mejor con grupos sanguíneos se puede, no lo sé, esa respuesta no la tengo, pero sería interesante poder generar alguna terapia halogénica que te permita no esperar 60 días para tener un material que pueda ser de utilidad clínica.
Gracias, Paul. ¿Tienes preguntas o hago yo la última?
Yo me voy por un comentario. I think that to have the mechanobiology right with the microvasculature experiments, you should have at the same time a soft substrate, but also a pulsatile flux. And I think a lot of the chips that have been made in Landsbiodet recently can be used for this kind of dual systems, where you can submit it to something that looks like the surrounding medium, the surrounding material, but also to the real stress condition by the blood flow. That's the first comment. The second one is that we have a current project with Landsbiodet about testing NK cell versus target interactions to follow the killing. And a colleague in France developed a software, an entirely new software with AI embedded, to detect the interactions between NK or T cells with target cells. And I think this could be a very local bridge, because you could test the efficiency of your CAR T cells directly in Landsbiodet with the softwares that we have, or with the techniques that we have, as a preliminary result to use them further on. The only thing you need is a semi-physiological target that is easy enough to handle, and something like a label, like PI, for example, or IP, I think it is in English, for seeing the cells dying, basically. So this could be very easy bridges to do. And for also I see things with the 3D micro balls of cells. This could be cultured in microvials, but means in surfaces where you texture the substrate. This is done, in fact, in Julien's lab. Julien is the next speaker who just joined. There's someone who does that. In fact, they made small traps where the organoids can go and be trapped locally. So you can even have numbers, and you can choose to recover them, the one that interests you. In fact, it's a semi-parallel way of culturing, but also more refined way of keeping an eye on a given system. Because the main difficulty is that they will look all the same. If you put them on a grid in small wells, you can really see who is who, and potentially culture different ones with the same environment, so that eases the controls and so on. So it's the way I think the micro tools that Landsbiodet are providing at national scale could be a very local use for you, and a very interesting interaction. I see these 3 points: microvasculature under dynamic condition using the pumps that have been made easily in Landsbiodet, culture in control conditions made in microsystems, and free testing. What really interests me also, testing these CAR T cells as killing a cell on culture, on mechano-bio control conditions, for example, with targets on hard substrate, on gels, targets that have been adhering this way, that are expressing this kind of lateral interaction, or discrete targets, to see the effects on whether the CAR T cell will be able to kill a micro tissue, a micro metastasis, or a flowing cell, if the cell is alone, for example. This is something that is not clear. At which scale is the CAR T efficient? And what are the limits?
Sí, gracias. Pues yo encantado.
Siguiendo rápido la última, antes de entrar con Julián, y en este sentido sobre las CAR T, preguntan, mostraste datos de cocultivo, CAR T, RE. ¿Están utilizando estos sistemas in vitro para predecir eficacia o toxicidad de nuevas construcciones CAR?
Sí, eso es el proof of concept, saber si obtuvimos las CAR y si tiene citotoxicidad contra quien se supone que debería tener, ¿no? Que en este caso son las RE. Pero sí, por ejemplo, como decía Pierre, o sea, una de las preguntas que teníamos es, ¿y cómo identificamos en el cultivo cuál es cuál? Porque tienes que ponerlas en un reto, ¿no? Entonces, lo que hicimos fue utilizar red Dextran en las RE y, no me acuerdo cuál era el otro, uno verde en las CAR-T, que es transitorio, ¿no? La expresión son unas horas nada más. No tengo sí, aquí está. Es se los debo, pero bueno.
Having a method to see in which time frame the CAR T are efficient on model tumors, and also help
Exacto, sí.
guide the therapy on the back. And that's the project of Diana, Tatiana, roughly.
Sí, eso que acaba de decir Pierre, that allows us to identify at what time it was the best time to have this cytotoxicity for red cells. In this case, it was 50 hours, for example, no? This graph that we're showing here. Sí, no recuerdo cuál es el nombre, discúlpenme, pero es Dextran Red y el otro es MitoTracker con verde. Ajá. Sí.
Y ya por último, en el chip de guía axonal, ¿cómo estandarizan la dirección de crecimiento de los axones? ¿Es principalmente físico o utilizan gradientes químicos?
No hemos llegado ahí. La idea era inicialmente generar el cultivo, ¿no? La estandarización, y lo que sigue va a ser por gradientes de moléculas. Sí.
Pues muchísimas gracias, Paul. Muchas preguntas, muchas opciones de colaboración. Espero que sigamos trabajando y que nos reunamos, porque justamente creo que podemos hacer muchas sinergias con nosotros y con todos los que están justamente participando en este seminario, que tienen modelos en los cuales utilizan unas u otras cosas. Muchas gracias, Paul. Esperamos verte por aquí de visita.
Por supuesto que sí, gracias.
Muchas gracias. Pues me voy a introducir Julien. Julien, te puedes hablar en español para empezar y también seguir siendo en inglés para la ciencia.
A ver. ¿Me oyen? ¿Sí? Ok,
sí.
ok.
Perfecto.
A ver.
So Julien is a professor at École Polytechnique here close to Paris in France, and we are working closely together on mechanotransduction, and is a professor of mechanics. He will present you results about his favorite technique that is based on micropipettes. It's not only the micropipettes that you would think of in terms of in vitro fertilization or single cell manipulation, but he made really advances on the way to use them for qualifying mechanics and for the how to say. In fact, we all use fluorescence when we look at biological systems. And I think what he will try to explain us is that fluorescence is not purely nucleus. In particular, when you go for subtle things such as the way cells can understand their environment using the mechanics, for example, but not only mechanics, biomechanics. So Julien, when you want, you can share your screen and the floor is yours. And
yes, thanks a lot.
Lo que quieres como lenguaje.
Bueno, yo decía, gracias. No, el contexto es que yo he vivido en el DF yo estaba contando 40 años, literalmente, que no es 40 años, yo llegué, bueno, mis padres nos llevaron en México, que mi padre tenía algo con de economía, en colaboración con el país, y nos quedamos casi 3 años, y ahí es que fui al colegio franco-mexicano, y es que no estudié español, es que fue solo hablando, así que me dicen la gente que tengo como un acento un poco extraño, que se oye que no es castellano, pero bueno, ustedes me dirán, y yo voy a hacer...
Hablas muy bien.
Gracias. Que no tengo acento francés, es verdad, ¿no? No. Mi R es...
Sí, pero es difícil que a los franceses se les quite el acento, no importa en español, en inglés.
Bueno, ok.
Pero también a los mexicanos no se nos quita el acento cuando hablamos.
No se debe, mejor así. Ok, aquí se ve full screen, normal, ok. Ok, pues es un placer entonces de presentar esto, que es digamos, un efecto, se usa a veces la palabra serendipity, pero realmente eso era un artefacto total, y lo aprovechamos para entender qué estaba pasando y voy a explicar un poco más, pero primero yo estoy muy interesado en la mecánica y estoy empezando en español, pero es que me estoy llevando así. No, I think I will switch. Is that okay? What do you... Yeah, I will switch. Okay. So, okay, we're interested in cell mechanics. Cellular aspects, but we have been really focusing a lot on the mechanics of leukocytes. I'm interested also, I do this kind of scientific illustration with Blender. I kind of advertise because it's €0, it's a free open access, if it's a free software, which is really competitive with the big ones that are commercial. So if you're interested, you can email me if you have a question about it. And then more broadly, I mean, here the audience is probably already, I have nothing to, nobody to convince that it's interesting to measure the mechanical properties of cells, but here you have these examples of, if you need an example to really prove it's important, you have this red blood cells flowing. From time to time, you will see maybe few platelets, but really here there was a leukocyte. And if you go into smaller capillaries, you see these red blood cells that are really going through capillaries that are half their size, which is in a way amazing and systematically. So they must be very soft. And if they suddenly become stiffer, you have a huge problem in the system, which happens in some cases, of some disease for the red blood cells, but also the white blood cells in some biological stress situation, including the cytokine storm that we heard about during COVID. The white blood cells that can become stiffer, for instance, less deformable, and block the smaller capillaries, hence stop the respiration process, and it's obviously it's a huge has a huge consequences. Okay, I will focus on one of these white blood cells. This is another small accident. This is actually one of mine, and you can see they're really dynamics. And those are obviously, I don't want to be bad with red blood cells, but they are really not doing so much as opposed to the sophistication of these white blood cells, to all the functions they can have, how many things they can do in a way. I want to acknowledge, probably Pierre-Henri already acknowledged, that's really, I'm really happy to be part of this initiative that started by Pierre-Henri to, in a way, to make a network of everybody, at least starting in France, but now it's broader than France, working on the immunobiophysics, so these physics that are really inside the immune recognition. So, and within this, in a way, philosophy, I would say, I'm really interested in, as Pierre-Henri said, micropipette-based techniques. And I like to say it's really, I'm an old-fashioned guy, because if you look at the number of published paper over the time, I started here, this is PubMed data, I just took it myself year by year. This is the number of citing or using AFM and optical traces, so atomic force microscopy optical traces. You see it's actually quite really a parallel saturation of the number of papers, but also this is in log scale, 10 times people use AFM 10 times more often than optical traces, apparently. And this is the number of micropipettes, it started actually before in the 50s, and it's already mature since the 80s. So it's an old technique, I may say, but we actually continue because it's actually extremely handy and extremely valuable in some aspects. So that's why we continue, and we actually specialize on mainly use micropipette based techniques. So this is one example of a setup. I don't go into the detail, but this is where I will tell the story from actually the clinical point of view, which is not often the case. So this is what happened. We had, and I will don't go into too many details, but this is a very flexible pipette that is bent. Actually, you don't see the tip. And if you pull on it, you can pull on this microbead. This is actually activating. It's a Jurkat cell, so it's a T cell line. So basically, this cell is getting activating. This T lymphocyte is getting has its receptor engaged, and it is then grabbing this microbead with the antibodies and pulling on it systematically. We have published this kind of things already for some time ago. And then by having collaborators coming to the lab in Palaiso, we did, okay, we will do something we used to do in Institut Curie, where I did this in other systems. We will do the same experiment where we were measuring forces and dynamics of the cells by imaging simultaneously calcium dynamics. And this is in a way a piece of cake. You just incubate cells with a fluorophore probe, and then you image by alternating wide field illumination, transmitted light illumination versus fluorescent, epifluorescent cell. When we did that, the cells on the right part totally stopped. Okay, it's a different cell type, the bead is a bit different, but really there was no reason. Something went awfully wrong, and in this case, it was a different cell type, so we became crazy. I mean, it was real collaboration, people coming from New York, it was had to work. And the only thing in the end, what we realized, that we said that, if I may, shit, it's the fluorescence. It's the only thing that we changed. We removed the fluorescence imaging, and boom, it worked. And we had our measurement. So since that, this was some kind of where I remember the pain of the moment, and I really wanted to do something about this. And I really wanted, I kept this in mind, so I want to go back and understand what's going on with, in some cells, in some settings, fluorescence is really bad. And at the moment, I thought it was fluorophore is really something to avoid, it's horrible. In some situations, and I don't know why, I used to work with Fura2 for the specialist of calcium imaging. I had no trouble in the past. So I wanted to understand. So the question was there was first an hypothesis, what we thought the cells were really round and not moving and developing their protrusions as we saw when a cell is getting activating, as if it was frozen. It seemed really rigid, but it's purely visual. Of course, if you want to prove that, you need to actually measure it. So we used again micropipette device, and this is I hope you see the movie running on the right, but just tell me if it doesn't. On the right hand, what you see is it's a T cell again, so this T lymphocyte. By the way, it's a really, really soft cell. It's typically part of the softest you have in the body with neutrophils. People say in the brain, but actually we should revisit, because the way to measure stiffness has a bit evolved. They said it was the softest. I could claim, actually, I'm not sure. Probably the neutrophils are even softer, and the T cells are really one of the softest part of them. Typically, we mentioned the effective stiffness. We use one lump parameter, which is a Young's modulus. That's like the elasticity of a material. We said the cell is a whole material, and it's typically 100 Pascal. That's the unit we use. So Pascal, the same unit as pressure. If you take a thick, a more stiff immune cells like a macrophage, you would get typically several hundreds up to 1,000 Pascal. And if you take your skin, you can go, cells of the skin can go up to maybe tens of thousands of Pascal, tens of kilopascals or a bit more. So it's a really soft cell, and it's a non-adherent cell, so we need to grab it and then to press it with a really controlled and not too much, not too large force. So the idea is really the same as in atomic force microscopy or other force measuring devices. Here on the, well, on this side, for me, it's my left, but on the screen, at least, what we are moving is a cell that is just gently aspirated by a pressure gradient inside the micropipette. And the cell is pushed, again, this, which is a glass bead. And this glass bead is the very tip, also very long and very flexible micropipette, which is shown here also. You see also, if you don't see my the arrow of my mouse, tell me also, because I'm showing here the micropipette. So here, this is a very long micropipette that is used as a flexible cantilever. So it's behaving really as a linear elastic spring, meaning that if I measure how much I go on this direction, how much I bend it, I am measuring actually the force I am exerting on the tip of this, it's a force probe in a way, this cantilever. And by axon reaction, there is no inertia in the system that are so small. The cell is feeling exactly the same force, but on the other direction. So here, by measuring how much we deflect over time this micropipette, we are measuring a force exerted on the cell. Now, if we measure, again, the same position of the tip, but we subtract the position of the piezoelectric stage that we control, we decide where it has to be, it's moving with constant velocity here. We can measure how much the cell is getting indented, how much it is deformed. And if you measure a force and you measure a resulting deformation of the cells, you can plot typically a force versus indentation curve. So again, the force applied by this whole bead on the tip of the cell. And we measure the indentation here, how much we deform this spherical shape of, it's called delta in microns. And if you plot this force versus indentation, it's not a linear curve. It doesn't need to be. Even if the cell behaves as a purely elastic material, it will be nonlinear because you are indenting with something which is not a point force or something flat. There's a curvature. But anyway, this is expected to be this nonlinear like this. And if you fit force versus indentation, and if you assume, we know it's wrong, but if you assume that the cell is behaving kind of as a pure elastic material, we know it's viscoelastic. We're actually working on this, but as a first approximation, it's fair, where you can fit, and actually the fit is pretty good, you can fit this curve and extract one single parameter, which is the stiffness. I will call it stiffness now on, but it's this effective Young's modulus. Effective because you know it's not the only parameter because that's actually viscoelastic. But to really be faster, I would just say this is the cell stiffness in Pascal. Okay, so this concept of measuring the cell stiffness, beside this really issue of effect of fluorescence, it's something we work a lot on it, on really different systems with different, meaning different cells. This is another, this is actually a Jurkat cell again, this T cell line that can be infected by bacteria from Listeria, but if one enters the cell, actually the stiffness is jumping from typically 100 to let's say typically 400. Only one bacterium can totally mess up the inner cytoskeleton. And I mean, we have a lot of things. We can also look at cells from the side to measure, to work on adherent cells. But to be honest, it's a bit of a trick. It's more complicated. The really relevant technique here would be atomic force microscope, because it's really meant really well sought for adherent cells. And last 3 examples, but here this is really something really, this kind of small beast here is actually a parasite. It's much stiffer. We are talking about differences. This is what I should remember, but typically at least 100, maybe 1,000 times stiffer than this cell. And we have a word on that because this is again a collaboration with Pierre-Henri and Aurélien Dumaître, who is a specialist of parasites in Pierre-Henri's lab. And here you can do a bit, even go further, this just measuring the stiffness. I showed you already a cell that was grabbing a bit, we were measuring forces. Here, this cell here, it's a neutrophil-like cell line. It is actually eating, it's phagocytosing this bead on the left. Meanwhile, we are pressing it in the back, if I may say, so that we can measure its stiffness over time during the process of phagocytosis. And using these kind of techniques, we have shown that during the activation of T cells, but also the activation of B cells, and also of phagocytes, during these activations, even though biologically is quite different, but the T cell dose, the B cell dose, or phagocyte dose, they become stiffer. There's a really huge change in stiffness, typically a factor of 3 to 10. It's really not just a 20% increase, it's really larger increase. So also that's the context we were used to and interested from the beginning in changing stiffness of cells. So that's why you had all the tools, and all these studies came through several collaborations. This is just because actually it's really nice. We had a lot of different projects. Just a word on these parasites again, and to finish over the technique. We can do, once we have this tool, we can modify it in an interesting way. In a way, instead of pressing a bead on the tip of the micropipette to measure indentation, what we did is that we modified the bead into something really sharp, a sharp needle. And by using this, you have a needle that can be able to really poke a stiff object, and while measuring the force you exert, which is the same concept. And here what we're doing is that we are piercing the wall of a parasite. I don't know if Pierre-Henri did or will, but I mean, this is an ongoing thesis in collaboration with him. And here what you get is the force needed to rupture a wall, which is quite different from stiffness. Stiffness is a whole material property, but the rupture property is something which is complementary. It's not the same thing. They are related, but there's not the same thing. And it's really interesting that we can get this in these parasites. And we are lucky in a way that if we kill the parasites, if Jana here kills the parasite with one way that could be bleach or heat or a combination, this force actually changes, which is not trivial. It means that we get information on the structure of the wall, which is really difficult to get by only observing, including with electron microscopy. Okay, so I can move on. Yeah, okay. Sorry, I'm because this audience you might be interested also in this subject. This is actually, it's not strictly speaking a spheroid. It's actually a model for skin, but this is done in collaboration with, should know his name. So Elisa Lenzi and Nadia Verti-Quintero, and this is in Charles Baroux's lab at Institut Pasteur, who is in between Pasteur and the LADIX, the hydrodynamics lab where I am. So this is a much larger object. This is typically 100 micron, and same technique, same concept, except that this is a much stiffer indenter. And we can measure, again, the force versus indentation. This is the same formula as if we assume this is actually behaving even more like a pure elastic. And the fit is pretty good, and we can exert in a really robust way stiffness of these objects. And it's just interesting for them, depending on the maturation level, depending on if there is collagen or not, and so on and so forth. Okay, now let's go to read the question we had. Okay, we had an effect of fluorescence. It was killing, we don't know, but totally inhibiting the activation. So we speculated that it would be paralleled by a stiffening, but the cell seems to be so round that we thought, oh, it looks like it's stiffer. So we I will just, I think, yeah, I will show you first I think I will show you, sorry, the movie. Yeah, the movie is coming if it's not here, but the concept is really simple. I showed you already a sphere and this indenter. So the idea is that we perform two what we call cycles with just one indentation, two indentations, typically at this rate. It's not really not much faster, not much slower. And after the second one, which is only for reproducibility, we do it twice. We shine only 10 seconds of fluorescence excitation light. And let's say first, this is fluo4. So it will actually emit light into in the green channel, but we don't care. All we need is to actually stimulate the fluorescence of these cells that would be pre-incubated with the fluo4. And then we see just 10 seconds after, just 10 seconds, but in the light, I should say, it's epifluorescence, and it's an LED. It's not a laser, but it's still full power of LED. I mean, it's really high power, and also it's a 100x objective, so it's quite concentrated really on the cell, so there's a lot of light. We anyway want to boost and really push the system to really put the potential effect in really to the focus on it to really have a strong effect on whatever it is. And afterwards, after this is the damage, we will see if it is a damage has been done. We measure twice the indentation. So what we measure this way, I will, this is already, this is, I could, maybe I will, I mean, afterwards when I'm done, I can show you exactly just a movie on this, but I will have other movies. So in a nutshell, it's a quite catastrophic effect. I mean, I mean, I do this smiling, that's cool, but actually it's bad. There is a really strong effect of fluorophore, but I will show you again, and several fluorophores. First, DMSO, this is a control, and this is the Young's modulus that is shown typically, again, the control starts at 100 Pascal-ish. And before is the average of the 2 first cycles before any stimulation, this 10 seconds. Here it's a control, there is nothing. In 10 seconds, we just wait, and then we do it again. So there is a tiny, tiny, tiny increase. There's something when there is not even no light. But really something is, it's interesting, there's something, and is it just a purely viscoelastic effect because we press the cell? Anyway, it's a detail relative to what we will see. If we stimulate a cell that has no fluorophore, so purely a light effect and no fluorophore inside the cell, there is an effect already of blue light. So that will be 450 in that case for due to the LED. And if you use UV, even a bit more. Okay, we know UV is not great, but there is an effect which is also, it's significant, but it's not a huge increase in stiffness, although there is one. Now, if we take a fluorophore, I mentioned fluorophore, but it works. DCFDA is really, oh, sorry. Okay, I was just checking there is a chat. Stop me if there is an issue or whatever. Huh? Because I see nobody, really wave at me if I have an issue or whatever on the sound or anything. So, okay, and DCFDA, yes, DCFDA is, okay, it's a dichlorofluorescein diacrylate, but it's a modified fluorescein. I think maybe some of you already, it's an obvious one, but it was not for me. It's a modified fluorescein that is used to actually show the presence of intracellular ROS reactive oxygen species, because we had in mind, so this is not chronological, but now we know that stiffening the cell, we ask what it could be, and one hypothesis that you create ROS due to a phototoxic effect. That's why we logically went for a ROS sensor. So this DCFDA is supposed to show you by emitting fluorescent light in the green channel. It's typically a GFP block, so you excite in the blue, royal blue, and you get into green. The more green you have, the more ROS you created. If you use DCFDA without excitation during these 10 seconds, there is no increase, not even, showing that this effect is really small. Sometimes you don't even see it, it's not significant. Now, if you excite with the blue, this DCFDA, this is the median stiffness, and it's bad. On average, I mean, this median has been multiplied by 9.5, so you get you don't get 20%, you get 1,000% stiffer. You get from 1 to 9.5 stiffer in median values. So you can see these guys, they go crazy. And this is, there is a red flag, it's bad. And the interesting aspect is that the ROS sensor is a posteriori the one that creates the most ROS by phototoxic effect. So imagine it was yet an artifact in the artifact. The ROS sensor that is supposed to show ROS is most probably creating a huge amount of ROS by doing so. So it's not a problem for us. We wanted to have something toxic. And even though it's not definitely not a great ROS sensor, it's actually a really nice phototoxic agent that is actually showing this, what we call this photo stiffening effect. By using light and through a fluorophore, we stiffen the cells. And now UXT, you might know it well. It's the stain for, it can be used even on light stain. It's an intercurrent. It binds with DNA. T cells, it's a bit unfair because T cells are almost only one huge nucleus that takes, I don't know, up to 80% of the volume. So it's not like nothing. You stain a big part of the interior of the cell, but it has an effect. So stiffening is only, with big quotes, a factor of 4, stiffen the cell 4 times. So it's a catastrophe. Again, with a big smile, it's bad. It's really, really bad. And we wanted to, in a way, because of our ego was wounded, we wanted to go back to this experiment. We take T cells, we use this fluorophore, and we wanted to have even quantification is fine, but just a visual proof that it was getting totally. Now we call them these cellular pancakes, and you will see why. First, I will press this cell against a flat surface. This is actually, again, a big pipette, just a small vertical wall. And you will see that because it's viscoelastic, actually, it springs back slowly because it's really viscous, but it springs back like this. And the second time, when it's in contact, I will turn on the excitation light because this cell is full of fluorophore, but doesn't influence the stiffness. Now, if I turn on the excitation light, we will see what happens. So I think I rerun this one. Up once, no light. When there's a star, the light is on. Okay, this is the control, and you see it springs back gently. The cell doesn't care, it doesn't die. If you want to kill a cell like this, you have to be even more nasty than that. The cell doesn't die. Now, if we go second time, boom, the light is on. And it's the movie, it's running. And then you can see how we can make pancakes. You just need a fluorophore and a few seconds of intense light, and it's gone. You see a faint thing, but it's not, the fluorescent block is not on, so you're not supposed to see, you actually some bleeding of the cell, of the fluorescence. And it takes only seconds, and that's it. The cell will not recover from this plastic deformation. So it has become, at least qualitatively, really, really rigidified. And we quantify the springing back without light, but with light, you cannot even quantify it. It's just, at least within this time scale of 15 seconds, it should have spring back, and it's here, it's not even moving. So maybe after minutes, maybe, but it's not even, okay, the point is made in a way. Okay, then, of course, we became paranoid. And we say, okay, T cells maybe, it's known actually that leukocytes, also migrating cells might be really delicate. And it's actually by discussing with colleagues, including in Pierre-Henri's lab, by asking, do you have seen this fluorophore effect? And said, oh, yeah, we know. If you have fluorophore and you shine the light, they stop crawling, they stop migrating. So I guess it's also difficult to publish as it. So in a way, it's known, but it's so okay. So for leukocyte, now we ask, okay, what happens in other cell types? So well, this is yet another leukocytes. PLB cells, it's a immune cell line. It can be differentiated in neutrophil-like. By the way, the cool story is that, again, a frightening story. To differentiate them into neutrophil-like, all you need to do is to incubate them is DMSO. DMSO is usually your control. It's actually a so-called, it's inert in principle solvent, but actually if you put a bit more than usual and you wait overnight, they start differentiating into neutrophil, which is frightening again, and reminds you that controls are important, and it's important to do these DMSO controls. Okay, so these cells, one has been or not differentiating, we did exactly the same. And here we went for the beast of this DCFDA because it was the largest effect, maybe for facility, but they were becoming, sorry, I moved my up. They were becoming only 5 times stiffer, maybe less than the T cells, but okay, it was a huge effect. And we went for endothelial cells to really change the direction, the really type of cells. And these are much larger cells. these are endothelial cells that can be trypsinized. We are not really, you know, I showed you you can indent different cells, but it's a bit complicated. So they have been detached. So it's freshly detached. And we have this control that before, after, without excitation of the light, it's totally fine. We are already much stiffer, typically 300 Pascal. It's stiffer than a T cell. But again, the CFDA is having this factor 9 of increase. So it happens, at least with DCFDA, it happens in 3 cell types. So maybe DCFDA is really bad. But I mean, we also tested different fluorophore in the case of CD4 T cells. So we also know that this one type of cells, several fluorophore are bad. Some are worse than others, okay, but the effect is there. And this is in a way another way to revisit our artifact, but maybe a bit more quantitatively. Here, what I will show you on the top is a T cell getting activated in the latest version of our setup. Here, this is again a really long and thin micropipette that is used as a cantilever. It is aspirating a bit that has the antibodies that is activating the T cell. Then we bring into contact the cell with the surface and we let the cell do its job in a way that does it push or pull. And the truth is now we have a feedback loop so that we can let the cell grow a protrusion, because we actually generate a protrusion against a control force. So let's run this. And the lower line is exactly the same experiment, except that when I will turn on the light, there will be a star, and you will see what happens to this protrusion. So on top, it's working. This is the normal thing. It grows this large protrusion and shrinks back. And on the lower left, when it stops, it's just that I turn on the light. And it's absolutely frozen. And we can quantify how fast it is. We turn on the light where the star is here, and then it stops. And we could measure almost the so-called slowing down, how much it really takes to really be totally flat. And it takes, when we use a full power LED, it takes less than 2 seconds. And interestingly, we have a dose effect. If we use 10% of the full power, it takes a bit more, it takes 4 seconds. Hence the idea to have a really full dose effect. I will show you this. This is just an interlude saying that, I will show you this to show you that phototoxicity, and in that case, we are interested in linking phototoxicity. So how fluorescence converts this interaction with the fluorophore with ROS, locally creation of, which is a really old process. Everybody is aware of almost very early from the beginning of fluorescence. Now we connect this to stiffening of the cell. But let's go back to not stiffening, but how phototoxicity is bad for some specific organelles. This is mitotracker. It's been just cited before. This one is orange, but okay. It's labeled specifically mitochondria. This is in endothelial cells. They are not in great shape, but let's hide it under the carpet. But these endothelial cells where we, with a 100x microscope, we can label specifically endothelial cells within only a spot that has reduced. It's only here where we shine the light that we actually see superimpose the fluorescence. And you can see also the destruction of this mitochondria. That totally, you can almost see the crystal because they're really blown up. And you can almost see the details inside. So it takes a few seconds to totally destroy. It's not stiffening, to be honest. It's a destruction here locally, and it's not totally trivial. And at the end of the movie, you start forming actually pores into the membrane. So we were aware of this, at least in adherent cells, but here it's complicated to prove that there's a local stiffening, and it's really actually, and here we also target only the mitochondria. So it might be that the rest outside of the mitochondria is not getting so much perturbed, even though the membrane here apparently is starting to form pores. Anyway, this is a small parenthesis, but we go into this, digging into this hypothesis that what we do is that we shine light on this fluorophore, we create locally ROS. And even though I showed you this ROS sensor is bad because it's actually having itself an effect of generating ROS. We will use this DCFDR to demonstrate that each time we press the cell, each time we press the cell and we shine light, in that case, instead of 10, it's 4 seconds, shorter times. We do a cycle, we do a snapshot of fluorescence, another cycle, we do a snapshot, and we show that we have, over the time, each value here, the cycle, is a compression plus shining light, except the 2 first ones that are actually controls without any, nothing happens before. The fluorescence intensity is increasing up to a saturation, and can be a lot of different artifacts, can be leakage or bleaching, but here at least it's increasing together with an increase of stiffness. So there is a really correlation between increasing fluorescence and increasing stiffness. In this case, we are gentle with the green to excite DCFDA, not so much. We are actually damaging the cell by it's a 2-color experiment. We are loading the cell with another fluorophore, which is cell tracker red, supposed to be a nice tracker just to look at the cytoplasm. Well, we are again coming with a big smile. Well, no, it's not that a nice tracker. If you put too much light, boom, your stiffness is increasing, and you are creating ROS. And here we are only trying to do a glimpse of fluorescence to just, let's say, exhibit the presence of increased fluorescence. This is, okay, so ROS, this is suggesting, and indeed we create ROS, and there is a correlation between creating ROS and stiffening the cells. Now the question is, can we create ROS without any fluorescence, independently of any phototoxic process, and see what happens to the stiffness? One usual trick is to incubate cells with a given concentration of H2O2. And surprisingly, actually, I didn't find it, but maybe because I didn't find look enough for, but I mean, if you put cells with a given, it's not a small, it's quite a big concentration of CD4, they become stiffer. So this works, you incubate them with a given H2O2 concentration, and I should have put it back, sorry, but endoterase 2, and yeah, and the last graph is you might think it's also, we did that in the beginning, say, okay, what happens in terms of molecularly with this ROS? What does the ROS do to link its presence with stiffening? We thought, we know it's been described that locally ROS can create covalent bonds between proteins or nucleic acid and proteins. And we thought, well, maybe the first target, because it's usually the usual suspect, it's a cytoskeleton. So maybe it's just stiffening the actin cortex. So what we did is that, okay, let's kill the cortex. So we did a big load of cytokeratin D and latracurine A. And actually the initial value, it's difficult to see, but it's much smaller. The cell is softer, and it doesn't care. If you load it with the same DCFDR, you give it the same treatment, it becomes even 20 times stiffer because it's starting lower, but it reached the same last value. So you don't care to have an intact cytoskeleton or not. It might be then a simpler story. So whatever is here as a proteic material and has maybe the proper residue, because cysteine can make bonds apparently, from my understanding from the photochemistry, but whatever is here, be it cytoskeleton or other nature, as soon as you have the proper residue, you might be able to cross-link. And then in a way, you are J-ifying your cell. And it's actually more specifically in the cascade of, in the photochemistry cascade of when you start and create a ROS, it happens that you create several side compounds, and one of them is actually formaldehyde. So locally, it could be that you literally fix your cells from inside, and then that becomes potentially interesting in terms of application, because if you localize light within a given organism, maybe, it's not obvious for the mitochondria because they seem not to stiffen, but to more be totally destroyed. But so obviously, it's probably more complicated than that, but you might be able in some cases to locally fix the cell from inside specifically. To be this, we don't know for the, we don't know if it's actually possible, really. So, okay, stiffening is independent of actin cytoskeleton integrity. And now I come to something also potential interesting, not to be too dramatic, saying, oh, don't use fluorescence, just use it wisely with a low. What people know already, you need to minimize your fluorescence signal to have just enough signal above the noise in a way to minimize your phototoxicity. It's not a new message in a way, but the fact that it's linked to stiffening is new to our knowledge. Now, some people want to create ROS, and it's in the context of photodynamic therapy. So the idea is it's a type of anti-cancer therapy that is being studied in a way. The idea is to put in cells. The question is to target this specifically in cancer cells. That's another question. But imagine you can specifically inject these molecules that are photosensitizers, and their job is to convert not bad, nasty light like UV. We use UV because it's nicely absorbent into the spectrum, but it also converts, let's say, a nice light like red light, which is supposed to be not really too aggressive for the cells. It converts it really efficiently in ROS. So the idea is to have, if you have typically a skin cancer, where you made it to deliver specifically the photosensitizer to the cancer, which is probably not such a trivial task. And now you can shine light, which is kind of non-damaging light, like a red light, and you will create a lot of ROS inside the tumor, and usually they use the light that they say, and it works, it kills the cells. Now we use the same. One of these photosensitizers is actually now an old generation, but it's A is one of these known photosensitizers. It's a derivative of the chlorophyll actually. So something that's supposed to convert efficiently light into chemicals. Sorry, and it works in a way that it makes the cell stiffer. And then we worked with a lab of Largibo, who is actually interested in how to vectorize this by using encapsulated photosensitizers. But here, in a way, okay, so the message is that this sensitizer creates ROS, but this is again correlated with a stiffening of cells, so opening the potential that why not using a local stiffening as, in a way, a proxy of a proper effect of this ROS generation, in a way. The fact that we would predict that it would be measuring the stiffness would be a proxy to measuring how much effect you have been delivered to potentially to the tumor, even though acknowledgeably it's a really early view of a potential application like this. So really, I will not go through too many. Well, I mean, just quickly, but I mean, we tested several fluorescent probes. So again, this shade tracker red, fluoro4, DCFDA, DCFHDA, those fluorescent, UX. And we also showed that actually there is a dose effect, stiffening, that is proportional to basically the number of photons you deliver to the cell. And there is an effect of this fluoro4 excitation, but a tiny effect also without any fluoro4, but that's in a way, here it's not the point, it's just a tiny effect. Interesting per se, but not the same question. And so we tested this hypothesis that's due to the ROS by creating ROS by a different manner by H2O2, and it also stiffens the cells, suggesting that's really the effect of the ROS. And again, if you look fluoro4 and T cells, I would say just be careful if you use something adjustive at 100x. Be careful with your dose, and have this in mind that if something wrong and something weird is happening, it can totally be an effect of the fluorescence. I will acknowledge, again, this work is in collaboration again with Jana was involved in some AFM validation. Pierre-Henri is in story. So I will also people from École Polytechnique, this LOB lab, Lorgibo for the chemist, the biochemist for the photosynthesizers, and other collaborators, and you for your attention. Thank you.
Thank you, Julien.
Thanks, Julien.
I will have just a short mention that the entire work is available on bioRxiv, but also will be published soon in Cell Reports Physical Sciences.
Yeah, exactly. Yeah.
You have the full story, and the stuff is, it's fairly detailed, and I think this kind of analysis of the artifacts that would come from the way you observe the system are very important when it comes to microsystems and biomagnetic stuff and biomechanics. And another note, Jana will be presenting on the 27th about the parasite that is a word that is just a site at the border of this BioPhysimmuno.
I hope I didn't spoil. There's a lot more than what just showed. Don't worry.
Yeah. So Tatiana, is there any questions from the audience?
So 2 questions that are related. I will say it together. Do you have evidence that the increase in stiffness depends specifically on ROS generated during fluorescent excitation rather than on local heating or non-specific photo damage? And in this same context, I imagine they are talking about the fluorophore suddenly freezes the protrusion during T-cells activation. Do you know whether this stiffening acts directly on the actin cortex or if it is mainly mediated by ROS? Both of them, I think, are linked. No?
No, exactly. So perfect. And so these are really healthy questions in a way. It's good to doubt that, okay, isn't there an artifact? So we tried to be as exhaustive as we could, meaning that we did cells without fluorophore. We used the same excitation light. Cells with the fluorophore, but without excitation light, to show that if the indentation itself has an effect. And then the last control is cells with the fluorophore and with excitation light. And it was day and night. You need both the fluorophore and exciting it with this proper wavelengths. And to go against myself, I should say what we did not do, for instance, is have a fluorophore and excited where it is not absorbing. Why not? It could be, but it should be this kind of effects should be. We think that here it's a bad light, it's creating ROS, most probably UV, and we see an effect, but it's a 50% increase. In some experiments, it might be considered as a lot, but we see again here 900% increase. So in a way, we don't care, it's fine. Okay, there is an effect, but it's really qualitatively a different thing in terms of the mass of ROS, if it's ROS. And so we are not sure that what we could do else. I mean, if there is heating, we have it without a fluorophore, so it's not that. But there could be something we missed, but I'm not sure here. I think there is a simple explanation: is that it's really you need to shine the proper light on the fluorophore. But I mean, there's still potential gaps that we missed. And the other thing, in these T cells, I don't know if it's only actin cytoskeleton, but if you destruct the cytoskeleton, you will not see the protrusion. So it's a difficult thing to test. But what we also know, I'm looking just for this. What we know is that this is actually with Claire Ivreau, so the collaborator of always on T cells from this kind of studies we know that this is a tube of thick wall of actin. There is no microtubule here. There may be a bit of cytoplasm. So this is a lot of actin. And indeed, I think this has become stiffer. But what I cannot tell you is that whether here it might not be stiffer. But I would suspect, given what we saw, that again, it's a simple thing. Everything is becoming stiffer because fluorophore is also entering the nucleus. It's not a proof, but I would say that everything that locally you will shine light and there is some fluorophore. It's known that the ROS, when they are created, they act within nanometers and they react. So it's a really local effect. So I would speculate that it's really everywhere that it's becoming stiffer, but it's a bit complicated. In a way, in this other experiment, this pancake experiment, when we turn off, when we extract the cell just to play here, this seems also stiff, but it's not a proof. So yeah, but you need to have actin to have the protrusion. So in a way, you cannot test exactly as in detail as you wish.
Okay, thanks, Julien. And then we have when fluorescence is turned on, the change in mechanical behavior seems almost immediate.
Mm-hmm.
Is this stiffening reversible if the cells are kept in dark or no?
So you have a good question because this was a question of one of the reviewers. So we are not, we have a single cell. We are not great at keeping it for a long time because it's typically the depression is directly coming if you need to keep a cell for 2 hours and then another cell for 2 hours. It's really, but what we did is that I went for advice by Lord, chemist who did that for herself. I bought it's in the house, when in the back of the house you have a big LED spot that is used to shine the whole room, the whole backyard. So I bought one of these and I put the whole petri dish on it, and that's why that's a way to have intense light on the whole petri dish. And then in the dish I tested many cells. But actually, when you put the numbers, because we bought a power meter, we needed to keep it for 20 minutes to have something equivalent in terms of number of photons of joule delivered by cells when compared to the 10 seconds of the 100x, to give an idea how the 100x microscope. Well, if you have a 4DX, it's also going to be, it's just concentrating a lot. So we did that, and after I think we have a 1.5 hour time point, we didn't see any difference, but we acknowledge we also started to see some apoptosis, some kind of side effects. So we don't think it's reversible within the time scale we looked at.
Okay, thanks. And then in the 12-cycle 2-color protocol,
yeah,
stiffness keeps increasing even when the fluorescence intensity does not rise proportionally.
This is another question by another reviewer. You can congratulate your audience because this is a cool question too, and this is again a fair question. But here we have, I'm not sure it's. Yeah, we looked at the dynamics of just this DCF fluorescence peak over time, and here there are a lot of things that could happen. You could have a bleaching of the fluorophore. Doesn't mean it. Here there could be leakage because potentially you start having this wall in the membrane. Why not? Even though we never had a bleb. So, and it's also known that this fluorophore is highly nonlinear. It's not a great tool to to have a quantification, but so here I suspect several things could happen, including just bleaching. So I would not bet that here there are less ROS being created. Here I would not trust anymore the fluorophore. So I wish, but I don't have a proof that you can exclude that you continue creating ROS. It's totally possible.
Thanks. And then in the before-after protocol, how do you control for cell-to-cell variability across cycles, considering that the indentation itself may alter the mechanical state of the cell?
Yeah, so depends exactly what you mean, but here what we have for each cell, we press it with a given the same maximal force. We do that for 2 cells, 2 indentation in a row. Then we have the treatment and 2 indentation again. The cell, there is variability, but not so much. I mean, if you take T cells, actually, if you take, there is a expected log normal distribution, which sounds like really frightening, wide, super wide. Okay, it can be log normal, but not so wide. So basically, we have variability, which is actually here. It's typically, this is our variability. So it might be log normal, but actually, it's not here. You will never, ever, ever have a T cell that is a kilopascal. And just because I like this, you will see that in publications. And if people tell you that T cells should be 10 kilopascal, me and Pierre-Henri, we have seen it, it's wrong. It's just wrong. The way they measure, I'm sorry, no, it's wrong. Anyway, that's the small message for, because there is a spread of, it depends a lot on the technique. To be nasty with Pierre-Henri is usually AFM people that get it wrong. No, because no, just for that might be useful as a remark. If you test cells with a really sharp tip, and if you go super fast, there might be even adding artifacts that add to each other so that you really, really overestimate the cell. And if you take it gently as we do, like you press it like this, you realize, no, it's not 10 kilopascal. So in a way, to go back to the question, I don't know if I answer it exactly, but we have variability, but the effect is so large, and we run a statistical test, even though we don't even need to, that, okay, the variability is also increasing here. Why? We don't know. It's not obvious that the cell had a lot more of fluorescence, is much stiffer. It's not that clear. And this is a cool question too. Why do cells in a way are protected? We don't know that. That would be a super interesting to know, but I don't know why.
Well, and 2 last really theoretical questions. One is there a physical model that relates photon dose, Ross production, and the increase in the effective Young's model, or not?
Yeah, Young's model. So not to my knowledge, there have been studies on effect of radiation. Some people have been radioactive tracers. And the idea is that you were breaking a cytoskeleton, and then the stiffness that emerged was actually decreasing, but decreasing by a factor, let's say 20 to 50%. And and here, I don't think they were actually modeling it, but it was just an observation that was against the opposite way. But I think what it could be that if you go to a small dose, first the cell can recover and can fight Ross. So it could be that it fights a given thing, and even to keep it, let's say the homeostasis, keep its stiffness. I think we go overboard and we overpass any facility, any capacity. And then I think we create Ross in so many spaces that we cross-link whatever it is. And even if the cytoskeleton is damaged, everything is cross-linked. I mean, at least we speculate that. So it's not even a problem anymore. I mean, it's too late. It's too. And then the modeling of this, not to my knowledge, not at all. And it would be, to be honest, what I would love to have is an idea of how to prove that you create locally covalent bonds. And this, okay, it's not a good answer, I mean, to a theoretical question, but I will have to have maybe a chemist who knows how to really prove that. If it's mass spectrometry, I don't know on single cell level how easy it is. So, yeah. So I don't answer well, but no, to my knowledge, not really.
And the last one, have you observed specific energy or intensity threshold where stiffening begins, or is the response essentially linear?
Within our resolution, I would say here it's not a threshold, because here it's just we don't shine light on purpose for a control, and from the first cycle, as soon as we shine light, boom, it's increasing. Here it's a small value, but the fluorescence is increasing. And I think I have the graph here, but this is Young's modulus versus fluorescence. And here, this is the healthy cell without fluorescence. We absolutely do not have any threshold apparently, which is, no. It could be actually also that if we were to go super nice, tiny bits of light and let a lot of time to recover, that the cell is actually recovering. But that's not exactly the same question as the threshold is. How can we quantify the recovery of cells and the mechanisms to fight ROS? And it's just a side observation. The ROS had apparently the H2O2 had less effect on this PAB cell line. And they became stiffer, but we needed to crank up the H2O2 level. And that could be interesting because these PAB cells, these neutrophils, if I may say, it's not really neutrophils, but they are professionals in creating ROS. They kill by using ROS, massive local concentrations. And it could be that they have learned, with big quotation, to manage and to to manage a lot of ROS, so that they are professional in being able to fight intracellular ROS when needed, not to get killed by themselves. So it would be interesting to have, in a way, an inner probe of how you are able to defend yourself against ROS. But yeah, that's yet to be done, and it would be definitely by collaborating with some biochemists really being interesting in the question.
Muchas gracias, Rubén. Creo que fue un excelente seminario, lo aprovechamos todos muchísimo.
Gracias.
Y pues, gracias por conectarte y por darnos esta plática.
Gracias. Pues fue un placer y bueno, gracias otra vez.
Okay.
A todos los que están conectados. Pierre.
Sí, todos los que están conectados. Con ese acabamos por mañana y nos vemos mañana a las 10 horas de México, a las 5 horas de Francia, para otras prácticas de Marie Dessart sobre el efecto del colesterol en la activación precoz de los linfocitos, de un punto de vista de biomecánica, pero también de biología celular, y a Gaurav Varma, que trabaja con Laurent Limousin, que muchos han visto el año pasado en México, sobre una manera de analizar el efecto de molecular engagers a nivel de la interacción entre célula T o NK que luchan contra células de cáncer. Pues con esto acabamos por esta mañana y Tatiana
No, eso, muchas gracias. Conéctense mañana y pasado. Tenemos otras 2 pláticas y además, si les interesan estos temas, los esperamos en el laboratorio para poder discutir con ustedes y trabajar proyectos en colaboración. Gracias.
Gracias. Hasta luego.
Gracias.